Today we study X25, kinetic theory of ideal gas. The ideal gas equation is PV equals NkBT. The P is pressure, V is volume, N is the number of molecules, Kb is Boltzmann constant, T is the absolute temperature. Sure, this equation can be written only if the system is in thermal equilibrium. It works only if the number of particles n is very large. Sure, one cannot describe the statistical system with a few molecules. Macroscopic variables, temperature, volume, pressure for a sample of mass capital M should be defined well to apply the equation. That means that it should be in thermal equilibrium at temperature T. In that case, any sample within the large number of molecules have the same temperature, same volume, not the same volume, partial volume, has same temperature and pressure. The equation is valid whether the molecules are of single kind or multiple kinds. Sure, it works even if it is composed of many kinds of molecules. Number 2, velocity V, momentum P, and the kinetic energy of a single molecule may vary depending on each molecule. Yes, it is a kind of random variable. Macroscopic variables P, V, and T are defined as the average value. So average over very large number. Very large number. We assume that n goes to infinity, and in that case, the central limit theorem shows the uncertainty, that is a kind of standard deviation, approaches 0. So distribution is assumed to be concentrate at the central value. The momentum transfers of n molecules per certain time interval to the wall accumulate to construct a net force on the wall. So it is a container. Inside a container, there are many molecules. They hit the wall and bounces back. That is the source of momentum transfer. That momentum transfer is in opposite momentum transfer to the molecule and opposite to that direction due to the action and reaction that produces the pressure on the wall. Collisions of molecules are assumed to be completely elastic. Molecules are making collisions with wall, and sometimes they themselves make collisions. We assume they are completely elastic. They preserve their energy. Number 3, the volume of a mixture of gas samples of identical temperature is additive. Additive volume, we keep the temperature. If we keep the pressure, okay, if you can still fix the volume to add more molecules. In that case, pressure increases. If we keep the pressure the same, then volume is linearly increasing if you add more samples depending on the number of molecules. The pressure of a mixture of gas samples is additive if we fix the volume. If you fix the volume and you put more molecules, PV equals NKBT, so P pressure, NKBT, if V, if you fix the volume and temperature, you increase the number of molecules, then pressure will increase. The total kinetic energy of a mixture of gas samples is additive. Total kinetic energy, that is energy. And temperature is proportional to average kinetic energy. Consider a single molecule of mass m in an evacuated cube. So there is only a single molecule inside a cube of side L, moving with the velocity. At some moment, it is moving with the velocity x1 dot, x2 dot, x3 dot at t equals 0. Area of each face is L squared. The volume of the cube is L cubed. We assume that 6 walls are infinitely heavy and the collision of the molecule is fully elastic, which keeps the kinetic energy of the molecule invariant. Okay. Every bounce on the wall perpendicular to EI, for example, is E1. So this is the surface. Flips the sign of the velocity. Okay. When it bounces, the x1 component should be positive, but when it bounces back because of the energy conservation, our assumption of a completely elastic collision, so it flips the sign. The period of oscillation along EI axis, because of after it hits this wall, when it returns to this position, as far as the xi component is concerned, it travels 2L with the velocity xi. So tau I is the period of oscillation along the xi axis. Okay. If the molecules do not interact and the wall is perfectly even, then the distribution of the speeds is invariant. I mean, they change by sign only. If the wall is perfectly even. So the speed, that is the magnitude, speed should be invariant along the x, y, z axis, and they do not communicate each other, and they are completely independent. So it is not natural. We assume that they should be mixed up and the average value should be some concentrated at the average value. But if it is a completely ideal case, in that case, the three speeds do not change at all. So we need some interaction of the collision of molecules, and we can also assume the uneven face of uneven surface inside the wall. Number 5, the same situation. We draw 3 cases, x1, x2, and x3. Red one is, this is tau 1, this is a period of this oscillation. And you find the slope. Only the sign changes when it hits the wall. The slope is invariant. And x1, x2, and x3, their slopes are not changing. Okay? It's a single particle, an even surface, then the 3 components must be independent. Anyway, by making use of this fact, we can compute the momentum transfer. Momentum transfer to this side and this side. This is twice the momentum because mv, for example, this is initial and final minus mx1. So delta P equals the final subtracted by initial minus 2mx1 dot. That is a momentum transfer to a molecule, and due to the action and reaction, the same momentum transfer to the wall is positive sense. And in this case, the pressure applies to the left. In a similar manner, force applied to each surface can be computed by using the momentum transfer delta P divided by period of oscillation. And period of oscillation, this is the period of oscillation. We divide. If we multiply these two, mxi dot squared over L. And then we divide this force by surface area, then this L becomes LQ, and LQ is nothing but the volume. Therefore, pressure applied to a single wall is equal to the mv squared. Here, v, the ith component that is normal to the surface, ith component squared. This indicates that the kinetic energy is something to do with the product of pressure and volume. So PV equals something mv squared. We shall find that this will be average it, and to find this one to be the kinetic energy, average kinetic energy is to be considered as kBT. And if you have a number of particles that increase the pressure, so the right side will be replaced with nkBT later. So this is what we have derived previously. And pressure perpendicular to the EI hat should be the sum of this mv squared for number of molecules. They should be summed. Next, we sum and divide this one by the number of molecules. Then multiply n, no change. So this one becomes the average value of mv squared. Average value of mv squared along the x, y, z axis. As a result, if we do not consider the collision of molecules, and if you do not consider the unevenness of the surface, then the distribution of x, y, z axis, the velocity distribution, should be independent. However, if we allow the many molecules to collide themselves and the surface is not even, then eventually these three velocity distribution should not be different. As a result, that is called the equipartition theorem. Randomness of the three components of the velocity shows that pressure should be the same along the x, y, z axis. Every surface has the same pressure if a large number of molecules are present and they are in thermal equilibrium. So x, y, z axis should be the same for the kinetic energy. Kinetic energy due to the motion along the x-axis, y-axis, and z-axis. Sure, 1/2 is missing in here. Anyway, this is the average kinetic energy, 1/2 mv squared. That should be x, y, z component. And equipartition theorem, that means x, y, z axis component should not be different. So they are the same. So factor of 3 and pull out the single component. It can be x, y, and z component. Next, we consider binomial distribution. Binomial distribution comes from the expansion a plus b, and how can I expand this? K goes to 0 to n, a, k, b, n minus k, n factorial, k factorial, n minus k factorial. You're familiar with this expression, right? This is binomial expansion. We also have multinomial expansion. ABC, just to generalize this. And so on. So this symbol represents the binomial coefficient. Why don't we substitute of probability P and probability Q, whose sum is 1. So these two events are exclusive and complementary. That these either this or that, nothing else. Then Q equals 1 minus P. So this kind of distribution appears when you throw a dice. Then you have 6 faces. If you throw a coin, front, side, or back, either A or B, P or Q. We expect in this symmetric case, P equals 1/2 and Q equals 1/2. By the way, if you increase the number of trial, if you increase this number n very large, you can see the distribution normalized by I have multiplied the square root of n to this distribution. We have a fixed point, a special value, and then for a small n, it has a distribution of a wider range. As we increase the number of trials, the width of the distribution becomes narrow. If we increase to 1,000, very short. But what happens if we increase the number to Avogadro's number, that is 10 to the 23rd? It is a sharply peaked at the center. This is the explicit demonstration of the central limit theorem. According to central limit theorem, this is a statistical behavior of binomial distribution. The shape of the distribution becomes very similar to the normal distribution that is called Gaussian. And as we increase the number of trials, the distribution is concentrated at the central value. And the width that is assumed to be the uncertainty is becomes very small with negligible errors. That's the key point of the central limit theorem. And this central limit theorem is closely related to the thermal equilibrium of a many particle system. Let's see, as n increases, the distribution is sharply concentrated at the central value. In here, K over N is concentrated at P, 1/2. The figure demonstrates the case P equals to Q equals 1/2. P plus Q to the N is always 1, with K events with the probability P. A similar behavior occurs, sure. In that case, the central value changes by this one. As the number of molecules increases, the pressure of gas sample should have a sharp peak at the central value. The width of the peak approaches 0. The width of the peak approaches zero as we increase the number of molecules. That's the reason why at thermal equilibrium, any part of any part of gas molecule have the same temperature and has the same pressure. The reason is due to the central limit theorem. And central limit theorem is valid only if n should be very, very large. Number 8, find a false statement regarding the average kinetic energy of n molecules in a box. You assume that the center mass is at rest. This denotes the average over the number of molecules. Xi dot, this is a velocity along the x, y, and z axis. Averaged over, this one denotes k, the identifier for a single molecule that runs from 1 to n. Average value of the velocity via 0. But because it is a random, is either moving to the right or moving to the left. The population of moving to the right and moving to the left should be the same as n goes to a very large number. Therefore, signed value, any signed value, signed random variable must have the average 0. So average velocity of n molecules, where n is very large, should be 0. However, when we square the velocity or speed, that should not be 0. Symmetry among the three Cartesian axes requires that the sum, 1/3 of the sum. Okay, this is the basic idea of equipartition theorem. Therefore, for I runs from 1 to 3, xi squared should be the same as the 1/3 of the average value of the full speed squared. So this is the fundamental background of the equipartition theorem. 9. Find a false statement regarding n identical molecules of mass m in thermal equilibrium at an absolute temperature T. Xi dot squared is the square of the ith Cartesian component of the velocity averaged over the n point-light molecules. In a thermal equilibrium at temperature T, they are always the same. And if I multiply the mass of each molecule, they are still the same. And definition of absolute temperature. This is the definition of the absolute temperature. Twice the kinetic energy along the x-axis, y-axis, single axis, divided by Boltzmann constant. This is the temperature. Because these three values are the same, so in units of Boltzmann constant, we expressed the temperature. From this, kBT equals mx1 dot square. And why don't we multiply 1/2? 1/2 kBT is 1/2 mx1 dot square. And this one can be expressed as the 1/3, 1/2 velocity squared. So this is the average value of the kinetic energy. Therefore, if we multiply 3, then 3/2 of kBT is the average kinetic energy of a single molecule. Average kinetic energy of a single molecule is 1/2 kBT multiplied by 3. This 3 indicates the number of dimensions. The average pressure on every wall of the container, what we have just derived for the pressure is N V mxi dot squared. And if we substitute this one with kBT, we have reached the ideal gas equation. So very important point is kBT is nothing but mxi dot squared average. Because PV equals always NKBT, among PVT, only two variables are independent. Once you know P and V, then temperature is completely determined. If you know V and T, you can determine pressure. If you know P and T, then you know the volume. Find a false statement regarding an ideal gas consisting of structureless point-like molecules in thermal equilibrium. The pressure of the gas on every part of the container surface is the same. Yes, right. The temperature and volume are fixed, then the pressure is the same independently of the shape of the container. PV equals NKBT is independent of the shape of container. For simplicity, we have introduced the cubic box, but the same is true for any shape of container. kBT, memorize mx1 dot squared, mx2 dot squared, mx3 dot squared is kBT, is proportional to the average kinetic energy. Average kinetic energy is 1/2 m x vector dot squared, so that is 3/2 of mx1 or I dot squared. Okay, so that's the reason why 3/2 of kBT is the average kinetic energy of a structureless molecule. The number n of molecules must be large to have our ideal gas equation valid, because the thermal equilibrium is approached only if n is very, very large. 11. find the false statement regarding Avogadro's number. Avogadro's number Na is exactly defined. It is exact. It is exact. The number of significant figures of Avogadro's number is infinity. We have infinite number of zeros after this. A mole is related. Mole is nothing but the Avogadro's number to the mass of the individual molecules. So Avogadro's number multiplied by the mass of a single molecule is the mass of sample. That is called the 1 molar mass. 1 mole, mass of 1 mole sample. The number n, this is a mole, is defined by the number of particles divided by the Avogadro's number. The number of moles can be inferred from the sample mass. Let's see. N, by definition, number of mole is number of particles divided by Avogadro's number. If you multiply both numerator and denominator by the mass of a single molecule, this is the mass of sample, and this is 1 mole mass, that is a molar mass. Molar mass. So sample mass divided by molar mass is the same as number of moles. One mole of hydrogen atom, we know this is mass number. This is atomic number. Atomic number represents the number of protons in the nucleus. Mass number is the number of nucleons. Nucleons is either proton or neutron. Proton and neutron, they are almost of the same mass. Their masses are slightly different from each other. However, they are almost the same. So if you bring 1 mole of hydrogen atoms, then gram, you copy this mass number and attach gram. This is the source. This is the origin. This is the origin of Avogadro's number. It is a single atom is a very, very light. Because if you want to express this mass, you need many, many zeros. Very inconvenient. That's the reason why if you introduce this huge number, Avogadro's number, then you can just make use of mass number in units of gram. Gram. In order to use gram as a mass unit, we have introduced Avogadro's number. The reason why we have about, it is approximate. The reason is that we have isotope. Isotope has the same number of protons, but different number of neutrons. So a very few isotope has the different mass. That's the reason why the exact average is slightly different from this integer. 1 mole of hydrogen molecule. We have two atoms. Each atom has a single proton, and H2 has two protons. We neglect the mass of the electron, so 2 grams. 1 mole of oxygen atoms. The 16 is the mass number. Copy the mass number and attach gram. Oxygen molecule, we have 2 atoms, so 32 grams. 1 mole of atoms of mass number A is not exactly the same as A gram because there are small fractions of isotopes. Their nucleus contains the same number of protons to have the same atomic number. However, number of neutrons may be different. 13. We have ideal gas equation. The ideal gas equation can be expressed in terms of the number of moles. Okay. This one, N, can be scaled by Avogadro's number and multiplied by Avogadro's number. What happens to NKB? This one becomes number of moles and Na times Kb. Kb is a tiny number. This is a large number. So we scale up. So it becomes Nr. So R is exactly defined by Avogadro's number multiplied by the Boltzmann constant. So this is exact, R is also exact number. This is a number, dimensionless number. Therefore, gas constant R has the same dimensions as those of Boltzmann constant. The number of moles is the number of particles divided by Avogadro's number. Gas constant R is more convenient than Kb, Boltzmann constant, if one deals with N that is of order Avogadro's number. PV equals NKBT is applicable not only for a monatomic gas, but also for diatomic or polyatomic gases. That's true. KBT is proportional to the average translational kinetic energy of the gas. Yes, so 1/2 KBT equals average translational kinetic energy, right? While PV equals NKBT is unique, CV may vary depending on the structure of constituent molecule. Yes, CV may depend on the structure. Structure means if it is a diatomic or polyatomic, in that case, it involves rotational kinetic energy. That is 1/2 I omega squared. N should be very large so that the macroscopic variables P, V, and T can be defined. That's right. Find the false statement regarding an isothermal process. Isothermal, iso, the same, thermal temperature. So T equals constant. Isothermal means T equals constant. PV equals NKBT determines the correlation between P and V. P and V, temperature is constant, so P is proportional to 1 over V. The work done by the gas from the initial volume V to NV equals PdV, and P equals this one, and temperature is constant, so it is factored outside of the integral, and this is a trivial log integral, and NKBT multiplied by log N. To keep the temperature invariant, the gas must be supplied by the environment because we have energy conservation. Temperature is the same, so this one disappears. This work. If you work, you should lose your internal energy. However, internal energy doesn't change at all. The same amount of heat has been supplied from the environment to the gas. So delta Q must be the same as delta W, and that is already computed. The internal energy of molecules is invariant because the temperature is the same. 16. Equipartition theorem states that the three Cartesian component of the kinetic energy should be the same. So x1 velocity, x1 component of velocity squared, x2 component of velocity squared, x3 components of velocity squared should be the same. That means that 1/3, every one of them is 1/3 of velocity squared. We see this one repeatedly. Definition of temperature is based on the equipartition theorem. Divided by Kb. They are all temperature. In other words, V1 squared, V2 squared, V3 squared average should be kBT divided by the mass of a single molecule. So root mean square speed is defined by square root of velocity square average. That is root mean squared. So this is mean squared. Root mean squared. So root mean squared, if we apply the equipartition theorem, this one is 3 times single component. So this one can be x2 dot squared or x3 dot squared. And we recall that single component of velocity squared is identical to kBT divided by mass. So we have factor of 3, and kBT divided by mass is the RMS velocity, root mean square speed. So root mean square speed is the square root of 3 kBT over m. Why don't we multiply Avogadro's number to both numerator and denominator? And we recall that the gas constant is Kb multiplied by Avogadro's number. And Avogadro's number multiplied by the molecule mass is a molar mass. So the root mean square speed can be expressed as a square root of 3RT divided by molar mass. We have reached the point in here, the speed, average root mean squared speed of a molecule is at a single temperature proportional to square root 1 over square root m. This one indicates that heavy molecule moves slowly. Heavy molecule moves slowly with the square root of m. And actually, this one was not derived, but it was found experimentally by Graham. And it was completely understood based on the ideal gas equation. So molar mass of hydrogen molecule is 2 gram. We just have derived previously. Where is it? Here. An oxygen molecule in 32. Their mass ratio is 16. If you take the square root, it is a factor of 4. So its root mean square speed of hydrogen molecule is 4 times greater than that of the oxygen molecule. If a molecule is heavy, its momentum transfer should be larger. However, small molecule moves faster. Heavier molecule moves slowly to make their contribution to the pressure always the same. That's the reason why the ideal gas equation is also valid when you mix up the various gases. That's it for today.